Good afternoon, everyone. Thanks for coming. My name is Stuart Marks. I'm the project lead of the core libraries team in the Java platform group at Oracle. It's good to be back. I haven't been to Antwerp in several years. All right, today I'm talking about sequenced collections. I'm going to start off by talking about a little bit of overview and history. Not too much here, but I think it's necessary background. First, there's this idea of what we're now calling encounter order, which is that when you iterate the elements of a collection, that the order in which elements come out are specified. And that's not true of all collections. Some collections have encounter order and others do not. There's also a notion of internal and external ordering, which is not really well developed, but I think it's easy to think about. Internal ordering is where the ordering is determined by the values of the elements themselves. For example, a sorted set, the elements are maintained in sorted order because of the values of those elements. Whereas external ordering depends on the APIs that you use. The client of the collection can determine the ordering. So if it wants to put something first or last, it calls the APIs to do that. So that's called external ordering. So both of those are encounter orders, but the APIs the semantics for those are actually different. So if we look at the original collections framework when it was introduced into the JDK in version 1.2 all the way back in 1998, these were the core abstractions in the collections. There was collection itself, which is simply unordered. There's list, which is externally ordered because you can specify where things go in the list and they stay there. And they're also indexed by ints. So you can ask for integer, you can ask for the fifth element, for instance. Set is unordered and it also has no duplicates. And sorted set is ordered, but it's internally ordered. Like I was talking about a moment ago, the ordering is determined by the values of the elements themselves. And since the set, a sorted set, has no duplicates. All right, so that was a reasonably good range of semantics for the different collections, but there's some things missing. And people would ask about this from time to time, and this would be manifested in bugs that were filed, enhancement requests filed in the bug database, and then more recently in Stack Overflow questions and places like that. So there's no collection interface that specified things that were sort of mixtures of some of the things I discussed on the previous slide. For instance, there's nothing that was externally ordered but not indexed. There was nothing that was externally ordered but with no duplicates. And so sometimes people would ask, well, I want a collection that's kind of a combination of a list and a set. So for instance, I want something, people would say things like, I want something that's just like a list, except it has no duplicate elements, or with unique elements, as they say. Or I want something that's like a set, so that it does have no duplicates, but that is externally ordered. And so remember, sorted set is internally ordered, and so that doesn't fit the bill. So maybe you would want a set that is externally ordered, so the API gave you control over the ordering of elements in that set. Anyway, the problem, of course, is that there was nothing in the JDK that offered any of those. So in JDK 1.4, which was in 2002, which is still a pretty long time ago, the linked hash set and linked hash map were added. And that helped with this some, but it wasn't really a complete solution. So linked hash set is a set, and it's sort of externally ordered because what linked hash set did and still does maintains the insertion order. That is, it's ordered by the order it maintains is the order in which elements were inserted into the set. So that's good, but it's not really good enough because it's still lacking a whole bunch of operations. Like you can't add something to the front of a linked hash set, and you can't remove things from the end of a linked hash set. But there was another thing about linked hash set and linked hash map, which is that they're implementations. And what I was talking about previously, like collection, list, set, and map, the collection framework is a family of interfaces. And so there's no interface here. There's just linked hash set is a concrete implementation, and it just implements set. And so if you want to talk about the interface, you lose all the semantics of ordering. Okay, so what do we do about that? Well, fast forward all the way to 2023, we are finally adding more collection interfaces to the collections framework. So really, I mean, there have been enhancements over the years, such as the unmodifiable collections and streams and things like that. But there actually have been no new abstractions added to the collection framework itself since 2006. So yeah, maybe this is a long time overdue. So what we did add in JDK 21 was 3 interfaces: sequenced collection, sequenced set, and sequenced map. And the essentials of what are provided by those interfaces are the semantics are that they have a specified encounter order, and they encompass both internal and external ordering. The second thing they provide is a nice set of operations: add, get, and remove at both ends of the collection. And so I think you have to think a little bit, but it should be fairly obvious that a collection has a finite number of elements, and if it is ordered, then there has to be a first element, and there also has to be a last element. And so we provide add, get, and remove operations for elements at both ends of the collection. And so if you have a collection that has 2 ends, it's sometimes useful to iterate the collection in the reverse order. And so instead of just, there are actually some collections that provide reversed iterators, but what we did was we found that it was much more powerful if we provide a reverse ordered view of the original collection. And so I'll talk a little bit more about exactly what I mean by that a little bit later. All right, so this is the collection hierarchy as it existed prior to JDK 21. Sorry, the lettering is a little small, but if you go look at the JEP, this is covered by a JEP, and I have a link to that at the end. This diagram is in there, and you can study it. But basically, you see there are a few more collection interfaces that were added afterwards. But basically, you see collection, set, queue, and map, and sorted set and sorted map, and extensions of the sorted interfaces, navigable set and navigable map. And of course, list and deck are under there. And then it's sort of outliers at the bottom: linked hash set and linked hash map. As I said before, those are not interfaces; they are implementations, but they form part of the story here because those implementations try to provide some things that are useful when you're talking about ordering. Okay, and then so this is how we have retrofitted these interfaces into the collections hierarchy. And so the green items are sequenced collection, sequenced set, and sequenced map. And so if you look at sequenced collection, you can see that that's fairly high in the hierarchy because there are a bunch of things underneath it. In particular, it covers sorted set, navigable set, linked hash set, list, and deck. So things that are on sequenced collection. A lot of things implement sequence collection. So the operations that are on there end up being inherited all across the hierarchy. And then sequence map doesn't have quite the same reach, but it has the same conceptual, same concepts in it: the ability to add, remove, and get map entries at both ends, and also provide a reversed view. And that applies to sorted set, navigable set, and linked hash map. I'm sorry, sorted map, navigable map, and linked hash map. Okay, so let's dive into the interfaces. So this is sequenced collection, and this is the set of operations that are on it. You can see this is pretty easy to understand, I think. There's add first and last, get first and last, remove first and last. Okay, this nice suite of operations at both ends. I will note that these 6 method definitions were promoted from deck. And so deck still has these, of course, but since they've been promoted up into the hierarchy, they're also inherited by list, linked hash set, and navigable set. Yeah. Okay, and then there's this new method, which is, well, it's sort of new. The reversed method, which returns a sequenced collection. That is sort of promoted, but it's been renamed from a feature on navigable set called descending set. And so it has essentially the same semantics. Navigable set dot descending set provides a reverse ordered view or a descending view of the navigable set. So we've taken that concept, but the idea of calling it a descending set, it does not apply to, for instance, a list. And so we're using a much more generic term for this, which is reversed, which gives a reverse ordered view of the original collection. Okay, sequence set is pretty simple. The only thing it does is it inherits from sequenced collection, but it provides a covariant override for the reversed method. So if you have a sequenced set and you call reverse on it, you don't get back a sequenced collection. Instead, you get a sequenced set. And then finally, sequenced map is a little bit busier. You have to look harder here to see the same essentials. There's still the add, get, and remove at both ends, but the naming is all different. And I'll talk a little bit more about that later. But maps use different terminology, and so you don't add to a map, you put to a map. So new methods, put first and put last, do the obvious thing. Existing methods on navigable map, there's no get. There's just methods first entry and last entry that get the first and last entries. They just don't have get in them. And then in navigable map, remove is spelled pole. So that's a little odd, but the reason is that those return null instead of throwing an exception. And I have more discussion about that later. There's the reverse method, which provides a reverse ordered view, as before. And then there are 3 new methods which provide the typical map view. So if you're familiar with a map interface, there's the key set values and entry set views of every map. And so since this is a sequenced map, there are 3 new methods that provide sequenced versions of exactly those things. Okay, so let's talk about what it was like trying to perform some of these operations prior to the addition of sequenced collections. So let's look at how to remove the first element and remove the last element of a variety of different types of collections. So if you have a list and you want to remove the first element, you remove 0, because 0 is the index of the first element. Okay, if you want it, pretty straightforward. If you want to remove the last element, it's like, how many are there? Okay, so list.size -1, and then you call list.remove on that. So how many of you have had to do that, and how many of you have to do that all the time? Yeah, okay, yeah, everybody raises their hands. And how many people are irritated whenever they do that? Okay, everybody. Wait, more hands? How is that possible? Okay, yeah, so it's a small thing, but whenever I had to write list.size -1, and then pass it, I got a little irritated about that. So, so that's a minor pain point. Dec, as you can see here, adds remove first and remove last methods, which do exactly what you expect. Now, linked hash set. Poor linked hash set. Okay, so you can actually remove the first element, but what you do is you get an iterator from it, advance to the next element, and then remove it. And then, boy, if you want to remove the last element of linked hash set, you are out of luck. And then navigable set does have these operations, except, as I said before, the navigable family likes to poll things instead of remove things. Okay, so since in JDK 21 we took the family of methods from Dec and pushed them up the hierarchy, all of these now inherit remove first and remove last. So they're all the same. I'm not even going to show that, right? So in list, you can now say remove last, and you're done. So that solves everybody's problems, right? Okay, now suppose you want to iterate something in reverse. And it's not, iterating in reverse is not something you do every day, but when you do it, when you need to do it, you need to do it, and it's kind of irritating having to deal with it. And so you could use indexes, I suppose, to iterate over the list. What I've shown here is the list iterator interface. And so what we first do is create the list iterator, and position it at the end of the list. And then the usual iterator thing is you have successive calls to has next and next to iterate through the elements. So list iterator allows you to move backwards. And so you say has previous and previous. And so that's how you go backwards in a list. So, okay, that kind of sort of works. You have to use the old-fashioned style of iterator, except with a list iterator, but it's possible. Okay, dec is a tiny bit nicer because what dec provides you is what's called a descending iterator. So that's just like a regular iterator, except it starts at the end and goes backwards. But you still have to do the usual has next and next pairs of methods. Poor linked hash set, once again, you are totally out of luck. And navigable set does something kind of nice here. I mentioned the descending set view of the navigable set. If you want to iterate that, you use our nice enhanced for loop, and you just say, let's iterate. You can navigate, you can iterate the navigable set in reverse order simply by iterating its descending set view. And so we've renamed that essentially to the reversed method. And so all of these list, dec, linked hash set, and navigable set can now be iterated in reverse simply by using the nice for loop over the reversed view of your list or dec linked hash set. Okay, now suppose you wanted to get a stream of the elements in reverse. So in navigable set once again is very nice here. You just get its descending set view, call stream on it, and you're done. So that's really nice. Now list, you can do it, but it's pretty involved. So what you need to do is, remember that list iterator loop I had? What you need to do is you need to build an iterator around that, and then wrap that in a splitterator, and then turn that into a stream. And so I'll actually show the code for that a little bit later. Dec is a little bit easier because you can skip the first step because dec gives you a descending iterator to begin with, but then you still have to try to turn that into a stream. And linked hash map. I'm sorry. Okay, JDK21, you just call reversed to get the reversed view and then call stream on that. And now you have the reversed stream. And that, again, applies to all four of these interfaces. And so similar kinds of things go on in the maps. So if you have different maps, you can iterate the entries in reverse or stream the entries, stream keys in reverse using the same kind of techniques. Okay, now that we have some new interfaces in the type hierarchy, how do you use them? Okay, so you can start to see how if you ever used some APIs that were sensitive to ordering, there's always this question of what types you used. And so if you wanted to accept a lot of things in your method, you might use something like collection. But the problem with collection is that it does not specify any ordering. So you'd have to write in your documentation, you'd say, okay, well, this method processes the elements in the encounter order or the iteration order of whatever collection you pass in. And so the caller has to be careful and not pass in something like hash set, which does not have a defined encounter order. And so if you're processing things in some order where the ordering is sensitive, like last one wins, if you pass in a hash set, you've created a pretty hard to find bug, because if somebody adds an element to the hash set, that could potentially reorder things and then cause a change in behavior. So if you use the sequence collection instead, then what that does is it constrains the caller to provide collections that in fact do have a defined encounter order. Now the caller still has to make sure they're in the right order, but that's an important piece of semantic information you convey in your API. Now, if you're returning something that has if you're returning a collection that has a significant encounter order, then there's this question of what return type you would use prior to sequenced collection. So you could put things into a list, but sometimes you have, a list is clearly ordered, and it's certainly useful to pass those around. But sometimes you have elements, or you're generating them or something, and you don't actually have the list, or you don't want to support indexing because you're, just the way you're generating them, or you might have to go find them. And so you could use a linked hash set if you happen to have one, but then that starts to expose pieces of your implementation, which is a little uncomfortable. But anyway, now that there's sequenced collection or perhaps sequenced set, you can return those, and those give you the right semantics you want without exposing bits of your internal implementation. Okay, so I've been dumping a lot on linked hash set, and kind of rightly so. It was pretty deficient, and linked hash map suffered from many of the same things. And it was a little odd. I'm not quite sure of all the history of why this was done this way, but it was kind of uncharacteristic for the JDK because the collections framework has a lot of nice properties to it. But when linked hash set and linked hash map were added, they really were kind of outliers. And I think the first thing that people noticed was that these are just bare implementations, and they have some nice features that people want, but there's no corresponding interface in the collections framework. And there's no interface that corresponds to linked hash set or linked hash map. And so I think sequenced collection and the sequenced set and sequenced map interfaces fulfill that now. Another thing is that linked hash map has a couple special purpose policies baked into it. So it has insertion order and access order, and you pass a Boolean to the constructor to get access order. And that just enables some special behaviors. And then you can also subclass and override a method called remove eldest entry that will remove eldest means first in this context. And in fact, you can do things that have other side effects in that method as well. But that only gets called at specific times. And anyway, so those facilities are useful if it's exactly what you want to do. But if you want to do something slightly different, you're kind of out of luck. So that's the problem. Anyway, so I think that sequenced collections fixes all these problems because linked hash set and linked hash map have been enhanced so that they now implement the sequenced set and sequenced map interfaces. What's funny is that the internal implementations of linked hash set always supported this. Basically, linked hash set was a set with a doubly linked list running through all the elements. So in principle, the implementation could already have supported getting the element, it had reference to the element at both ends of the doubly linked list, and you could go in both directions internally, but that was never exposed into an API. And so sequenced set and sequenced map actually expose those functions that take advantage of the fact that linked hash set has a doubly linked list running through all its elements. In addition, linked hash, both linked hash collections have additional semantics for adding and putting at the first and last. And they're very carefully specified. It basically says, if you do add first, the specification says, adds this element to this collection. After this method returns, the element will be in the first position in encounter order. Sorry, did I say add first? But anyway, I think you get the point. If you say add first, then that element is at the first position. And so what that means is in linked hash set, if you add an element that is already there, it is also repositioned to be at the first position. And so you can use add first and add first, add last, put first, put last to reposition elements in linked hash set and linked hash map, which was simply not possible before. Anyway, so I think all these enhancements rehabilitate this class because there's a whole bunch of implementation there. It's just that it was not possible to get at them because there were no APIs that provided them. And so I think sequence set and sequence map provides those facilities now. All right, so I'm going to go through a couple demos here. So let me switch into NetBeans. I guess I'm one of the 1% that uses NetBeans. Okay, no, that's not the one I wanted to start with. Okay, so reversed is a view. All right, so Morris Nafton and I had a deep dive yesterday where we went into great detail about what a view collection is. But just to hand wave it a little bit, a view collection is not a separate collection. A view collection provides a facade in front of some other collection. And so reversed gives you that. It's just that it reverses the order. So if you have, and so what I have here is an array list, and I'm going to get a reversed view of it. That's not actually a separate collection. What it does is, actually, this is the output from the previous, sorry, from a different demo. So let me run it here and show you the output. Okay, so we have a list which has alpha, bravo, Charlie, delta, etc. And then an R list, which is the reversed, yeah, you can see my cursor there. Okay, so this is the reversed view of the original list. And so we print them out. And so you can see that the list has the strings in order, and the reverse list has the strings in the opposite order. A little wrinkle here: if you get the reversed view of a reversed view, you get the original list back. And that's not always true, but in most cases it is. So is that identically equal? Yes, it is. Okay. Now here we show that we're going to set element 2 of the original list to x, y, z, z, y. And so you can see that appears there. And then in the reversed view, it appears in the reversed view as well in the right position. Now I'm going to, in the final bit of this here, you can see the code there, but I basically printed it out. I'm going to set an element in the reversed view, and then it's going to write through into the backing list. So you can see that the reverse list has plu in that position, and that ended up in the original list in the proper position as well. Okay, so this is mostly just showing off this ridiculous implementation of how to construct a reverse ordered stream in the absence of sequence collections. You can see it here. Basically, you get a list iterator. So basically, I want to iterate, I want to get a stream of these elements in reverse order. So let me run this. And basically, the application is find the last string that contains the letter A. Okay, so that should be delta. And so if I run that, how come that's not running? There we go. All right, so I run it twice. I have an old version here and a new version. And so the output isn't that interesting. You can see, obviously, if you start searching from the end, delta is the word that has A in it. But this is remarkably painful. You have to take a list iterator and then wrap an inner class iterator around it that translates has next into has previous and next into previous. And then wrap that in a splitterator, and then take the splitterator and wrap it into a stream. And then you do now that you have a stream, you do the real work. You do the filter and find first. And so that's kind of lost in all the noise there. And so now with sequence collections, if you want to stream something in reverse, you just say list.reverse.stream. And then you just go on from there, filter, find first, and get the result from the optional, and that's how you get your result. Okay, and finally, this is a little strange. One of my colleagues, I'm sorry, it's not a strange example. It's a bit obscure. But one of my colleagues, I think this has to do with, he was working on networking, and he was like coalescing network packets to do defragmentation or something like that. But basically, he had he actually gave a talk to our group about this. He said he had a wrestling match with list iterator. And so let me talk about the problem a little bit. Basically, he has a list of elements of some sort. I think there were network packets or something like that, but I'm just going to use integers here. But the idea is that you have a list of these things, and some of them are markers. And whenever you encounter a marker, you want to do some processing on the previous element. And so if the previous element is greater than 0, you decrement it. But if the previous element is 0, you delete it. And he thought about this for a moment. He says, list iterator, I can do that. So basically, run through the list left to right, and when you encounter a marker, actually I'll show the code that does that. Run through the list left to right. When you encounter a marker, you have to back up over the marker, back up over the previous element, do some logic on it, and then either remove that element or write it with its new value, which has been decremented, and then depending on whether you removed it or modified it, you might have to advance over it again and then advance back over the marker. And it took him about 5 tries to get this right because the positioning that you have to do in list iterator is quite obscure. And so, but he finally got it right, and this is what he ended up with. And it's like I mean, it's not terribly bad, but you also have to be really familiar with the way list iterator works, especially when you're doing side effects on what's in the list. And so it turns out that if you iterate the list in reverse, it's actually quite a bit simpler. So if you're iterating in reverse, when you encounter a marker, you just make a note of that, and we say previous marker was, the current one is the marker just before we start the loop again. And then that means the next element is what you treat specially. And so I've done this slightly differently here. I'm copying the output into a new list instead of modifying it in place. But this makes it much easier. So if you run into a marker, you either decrement this element and add it to the output. But if the element is 0, you just don't add it to the output. And if the element wasn't a marker, you just add it as normal. So it makes it I think it's a lot easier to understand, and you don't have to do this navigation back and forth that you have to do with the list iterator. And here's the example. I mean, -1 is the marker. I think the example itself is not too interesting. I think that what this shows is that if you're using list iterator to try to do weird list surgery, especially if you need to go backwards in the list, maybe consider iterating the list in the reverse order using the new reversed method. Okay, back to the slides here. All right, so the rest of this talk is about design rationale. And how am I? Okay, so I have a bunch left. Okay. I think I mentioned this a little bit before, but actually I wasn't explicit about this. One of the things that I've tried to do very strongly in this design is to make sure to reuse methods from existing interfaces. I think there's some comments like, oh, you should have named this differently, especially the poll methods. I mean, the poll methods really are rather odd. But the problem is if you add new methods that are different from existing ones, then what happens is it kind of messes up, it potentially messes up interfaces that inherit these. Like so then you end up getting duplicate methods that have different names, but really have the same semantics, which just makes APIs more complicated. But anyway, in reusing those methods, I think promoting things up higher in the hierarchy is it's rare that you have the opportunity to do this, but when you do, what you can see that it does is it spreads that power across a much broader range of interfaces than you had previously. And so for instance, this solves the problem that people had, which was they have some things in a list, and the list is pretty powerful, but they said, oh, there's this deck over here that has, remove last. I wish I could use that. Well, now you can. Okay, so we did apply this to deck using add, get, and remove first and last. And I think I talked about this before. First entry and last entry, poll first, poll last entry for navigable map. And unfortunately, poll has slightly different semantics from remove, but that's what ended up being on the navigable set and navigable map. Okay, so here's a tougher one I spent some time thinking about. Suppose you want to call get or remove, and the collection is empty. What should happen? So these methods all throw exceptions, and in fact, so for instance, the add, get, and remove from deck do that, and so those are the ones that are propagated all over the hierarchy, and you can't really change the semantics. You really want to have the semantics remain the same. But deck has this. Deck is kind of a weird interface because it says, oh, well, if you don't want to have an exception thrown, we have a bunch of null returning methods. There's offer, peek, and poll are the alternative set of verbs. The problem is that those were added as part of the concurrent collections, the Java util concurrent stuff, and the Java util concurrent stuff is, as a rule, hostile to nulls. So the concurrent collections in general cannot contain null. And so there's this problem, which is if you use, say, poll first on an empty collection and it returns null, then that's not a problem for the concurrent collections because they cannot contain null. So null unambiguously means that the collection is empty. But if we were to take these methods and propagate them around, array list can have a null in it. And so you could say poll first, and if you get null, you might have actually removed the first element which happened to be a null value. And then you might say poll first again and get null. And you just don't know whether the collection is empty or whether you really did remove a null element. So that's the problem there with null returning methods. I forgot to mention optional. People say, oh, well, if there's nothing there, you should use optional. Well, since we're reusing methods, the deck methods get and remove, they don't return optional. So we're not going to change the return type because that would be incompatible. Okay. I went through that. All right. On the map side, it's different. The map methods do return null. It's like, well, isn't that inconsistent? Well, it sort of is, but it turns out that returning null is quite okay for a map because when you're dealing with maps, you're dealing with map entries. And a map entry is a key value pair. And so if you say first entry on a map, then even if one of the keys or the values is null, which is permitted by things like hash map, the entry itself is always non-null. So if you have a null key and value in a map and you say first entry, you're going to get a non-null entry out of that. And so you can tell, oh, and then of course if it returns null, you know that there are no entries there. So there really is no ambiguity there. So even though it's not consistent with the collection side, the map side returning null actually makes perfect sense. Okay. So I glossed over this, but if you remember the collections diagram, the class diagram from earlier, Q is a collection interface, and it is not included as part of sequence collection. Why is that? Q is ordered, right? I mean, usually you put things in at the end and take them out from the, well, you add things to the tail and pull things out of the head, and it maintains an order. Well, mostly. The first problem is that it's asymmetric. Most queues cannot add at the head or remove from the tail. And if you can, then it's a deck, and deck is included. But queues are kind of one way. And really, the way the queues are used in systems is for transmitting values between threads. So the collections that I'm talking about here are used for storage of values, typically in the state of an object. Queues are used for transmitting things between threads. And so it's kind of a different use case. So trying to apply sequence collection to a queue is kind of strange. But there's another thing too, which is that priority queue is a very strange collection. It kind of does and it kind of doesn't have an encounter order. And so what priority queue does is it allows you to add things to it, and it will order them by value. And so you provide a comparator to the priority queue, and it'll compare the elements, and it always returns the least element in the collection. The thing about priority queue is that this order is revealed only destructively. And so it's a heap data structure. And so you only get the elements out in order if you actually remove them. If you iterate a priority queue, you actually get them in a different order. You get a different order based on the internal heap structure in this array. And so this is a constant source of bug reports where people throw things into a priority queue and they iterate it, and hey, it's not working. It's like, well, that's the way priority queue works. And so really, the notion of encounter order that priority queue has is rather strange. And so it just didn't fit with sequence collection, so left it out. Okay, covariant overrides. So there's a language feature where if you override a method, then you can return a subtype of the return type that the overridden method returned. And so we take advantage of this with the reversed method. So if you have sequence collection and you call reversed, you get a sequence collection. If you have a sequenced set and you call reversed, you get a sequenced set. Same with list, deck, and navigable set, and probably a couple others as well. So I think this is really nice because if you have a list and you get the reversed view of it, you still have a list. And so you can operate it on exactly the same way as that you could the original list, for the most part. And I think that's really powerful. We didn't do that everywhere, though. So we did it with reversed because reversed is a new method that is appearing on almost all the collections. Yeah, in fact, it is new. It did not appear anywhere before. You might think that, I was talking about the map views, key set, entry set, sorry, key set values, entry set. If you have a sequenced map, maybe those should return a sequenced type. The problem is that there are existing implementations of map out there, including third parties, that override these view methods and do not return the sequenced type. And so it would in fact be incompatible if we change the return type of key set values and entry set to be sequenced. So for that reason, we added 3 new methods: sequenced key set, sequenced value, sequenced entry set, which do return the sequenced types. All right, there is some asymmetry here in this lovely, nice, symmetrical, uniform hierarchy of operations and types. You cannot call add first and add last on navigable set, and similarly with put first and put last on navigable set. They will throw unsupported operation exception, and people hate that. But unfortunately, there's few alternatives to this. And this goes back to what I was saying earlier about internal ordering versus external ordering. The navigable family of interfaces is internally ordered. Those elements are sorted by the values that they have. So you cannot put something at the first element. That would simply not make sense, because you can't put an arbitrary element at the first position, because when you put something into these, they will put it into the right position, not the one you ask for. So it simply doesn't make sense. There's a small design space of alternatives to this, but really none of the alternatives are reasonable. There's some weird things going on with conflicts of covariant overrides, right? So if you have covariant overrides and you have if you have a tree structure, then inheritance works, and anything that can override its supertype. The inheritance hierarchy of the collection interfaces is not a tree structure, it's a DAG. And the reason is that we have multiple inheritance of interfaces. And so, for instance, we have list.reverse returns a list, and deck.reverse returns a deck. Well, what happens if you have something that implements more than one of these interfaces? In fact, there is such a class, our good old friend linked list. So what do we do about that? Well, so the requirement is that the reversed method needs to return something. It can't be a list, and it can't be a deck, because that would always conflict with the other one. So it needs to return a type that is both a list and a deck. So we could come up with a new interface that is both a list and a deck, but that's not clear that it's worth it. The thing closest at hand that implements both list and deck is linked list itself. And so linked list.reversed returns a linked list, and that actually works. But it doesn't return the same linked list. It actually returns an internal subclass, which is a view that delegates everything to its backing list, but it's actually a subclass of linked list. So hey, it works, and nobody should be using linked list anyway, so you shouldn't bother with it. But overall, I actually did a search through a large body of code, and it turns out it's quite rare for a class to implement from 2 different families from different parts of the collections framework. So I don't think this is a problem. It's not difficult to deal with this, but it is kind of tedious. But I don't think it'll come up in practice very much. let's see, what was the, yeah, this was a bit of a, this is a bit of an implementation hack here. Oh yeah, I have time for this. Okay. So sorted set is a little bit underpowered. So sorted set was, actually sorted set goes all the way back to the original. If you look at the hierarchy, there's navigable set is an augmentation of sorted set that provides much more powerful stuff. And same with navigable map and sorted map. So when designing these new interfaces, there was this question of what to do with sorted set, because if you look at what the operations are available on sorted set, it doesn't seem powerful enough. And the reason is that if you're adding default methods to, in fact, all of this stuff I'm talking about, moving methods around, all of these are default methods. And so so that's how we can modify interfaces without breaking compatibility. But the general rule for default methods is that if you're adding a default method somewhere, it needs to be implementable somehow in terms of other existing public methods that are already on the interface. And so, because, how is it going to work otherwise? So the problem with sorted set is that adding, getting, and removing at either end is pretty easy, because those are those functions are available somehow on sorted set. But reversed is tricky. In general, the way to get a reverse ordered view is to get a descending iterator, and then you can build a reverse ordered view out of that. But there's no descending iterator on sorted set. There is a descending iterator on navigable set. In fact, navigable set is the one that has the descending set view. And so that actually is the reversed view itself. But it's not on sorted set. So how can you, the task became, how can you build, if you, given an arbitrary sorted set, how can you build a descending iterator of the elements in the sorted set without copying them all out and then reversing them in, somewhere? So it turns out there's this little trick here, which is, so there's a last method, which returns the last element of a sorted set. And then head set is an interesting API in sorted set. What that does is it returns a subset of the sorted set, which contains everything from the least element up to but not including E. So if you know that E is in the sorted set, you can ask for the head set of E, and that includes everything up to but not including E. And then you can call last on that and get the previous element from E. Okay, so if you start off with the last element, get the head set of E, and then get the last from that, you get the previous element. Now get the head set of that previous element, and then get the last element of that set, you get the previous element. And so now you have a reverse iterator of sorted set. So using this technique, I was able to bring sorted set into the full sequence set fold. So that was pretty nice, I thought. Now what you're doing is you're creating a succession of sorted subsets, but that's kind of expensive. But in fact, it does work. All right. I'm at the end here, right, and I'm running out of time. So great. So I think sequence collections, I hope you enjoy it, and because I think it provides a lot of useful functionality. It provides new types that you can use in your APIs that give your APIs more precise semantics. Provides a bunch of new operations that will enhance many collection implementations that exist in the collections framework, and it rehabilitates linked hash set and linked hash map, and I think you'll find that those are much more useful than they used to be. So for further information, you can look at the JEP that covers this, JEP 431, there's a link. Of course, this is in JDK 21. You can download it from there if you haven't tried it already. Or you can go directly to the Java Playground and start typing this stuff in. That's the interactive website where you can just type Java programs, and that's upgraded to JDK 21. And finally, if you would like to contact me, I am on Mastodon at that address. So thank you and enjoy.